So for the colloquium today, we are very pleased to have Ravi Vakil from Stanford, who will cut and paste in algebraic geometry.
So I'd like to thank you very much for giving me the chance to visit and to speak with you. My goal today is to introduce you to a notion I find very interesting, the Grothendieck ring, of varieties. And what I want to do is to try to tell you a little bit about it, and in particular I want to convince you that it's something that is interesting and why it's interesting, and in particular how it relates to various very natural questions. So then in the course of doing this, I'd like to tell you about a conjecture and a couple of theorems, but I'd like to concentrate on getting across what the larger subject is already about. In particular, I want to spend some time really on one example of something that I thought I understood in high school and learned that I really don't understand very well, which is the example of just points on a line, or equivalently of polynomials in one variable. What could be simpler than that? So I do want to say in advance that I'm taking this as a colloquium, not a seminar in algebraic geometry, and there are a lot of experts in this room, and I want to apologize in advance that my goal is to I'm happy to talk about it in greater detail after, but I'd really like to address this to people with wide mathematical backgrounds. So please stop me and ask questions, and if you have fancy questions to ask, I'm also happy to discuss them, but maybe more later on, since this story can get very complicated very quickly. So what the story is really about is one of the things that really attracted me to the subject in the first place, both algebraic geometry and more generally mathematics, which is this fact that there are these links between different parts of mathematics, and in the case of this talk, between topological notions and arithmetic notions, and that at least part of the story, part of this link, goes through geometry, through algebraic geometry. Okay, so let me begin with some general fun background. I'd like to start as close to the beginning as possible. So I want to define complex varieties. So let me first define complex affine varieties, by which I mean nothing more than subsets of C of the n that are cut up by a bunch of polynomials. So these should be polynomials. We're only allowed to talk about polynomials. I will deliberately not call the C to the n, I'll call it affine n space over the complex numbers for two reasons. One is I will not be able to stop myself. But secondly, I'd like to have in your mind your picture, but something slightly more precise. So that's an affine variety. What's a complex variety in general? Well, how do we define a manifold? What is a manifold? We take little pieces of R to the n, a real manifold, then we glue them together in patches. In complex variety, you just glue these together, and we use only algebraic or polynomial gluing data. So that's somewhat deliberately vague, but probably enough for what I'd like to say.
That or means i.e. Algebraic or polynomial.
I use algebraic, as in polynomial, or to be more precise, maybe rational functions.
As long as they're defined.
Exactly, as long as they're defined. So, exactly, and I'm eliding so much in doing that. But no e to the x's or signs allowed. Things you can write down with, in terms of polynomial.
But wait, if you're going to glue a whole affine variety together and you have a rational function, it would be zero somewhere at the bottom, so it wouldn't be defined in the whole variety.
So you might need open subsets, just like with manifolds, you glue them together, one open subset.
Open subsets of these.
Absolutely. And there's of course, even that's not enough. I'm admittedly being very telegraphic. But maybe the main thing I want to get across is that think manifolds, and think that you're doing this with one hand tied behind your back, because your functions, in terms of how you deal with what your open sets you're moving on. And if that was bad, I'll say something worse in a second, which is I'm going to want to work over a general field, and then I need to, if I were to be really honest, tell you what a variety is over a general field. And so I'm going to tell you something in terms of something vague, but I hope will be sufficient, which is that in particular finite fields are going to come up inside here. And so instead of, so you might think that you want k to the n, and there's a better version of k to the n, which is, this is, for example, k is a finite field, that's a finite set. There's a better version, and I'm not going to say what it is, but you should think of it as being analogous. I'm happy if you think of it as being analogous to this, and then you move with algebraic. And that's not, absolutely not enough for you to really go ahead and prove a theorem or read something about it, but it's enough to have you think about what I'm going to say. And as an example, there's, let me just mention briefly, so just definition by example, that projective space CPN or RPN is obtained by, we obtain this, one can obtain it by gluing together a bunch of C to the n's or affine spaces together in an appropriate way. And in this vague statement, the way it is appropriate, it is algebraic in its appropriate sense. And so similarly, you could have projective space, and you want it instead this way, over an arbitrary field. Okay, so now let me get to the ring I'd like to discuss. And this is the Grothendieck ring. Of varieties, and again, you can be welcome and encouraged to think about the complex numbers, mainly, since that's my preferred home as well. And so this is a ring that's obtained by cutting and pasting varieties. So let me say what it is as a group. It's generated by symbols, or by classes of varieties, symbols where the x is a variety of isomorphism. Now I'm fixing field, I should say. This is for varieties over a fixed field. So these are the things you can, as a group it's generated, it's an abelian group, I should say. It's a ring, so as an additive group, it's generated by these. I'll tell you how to add. The additive structure is generated by the following thing. If you have a closed subset and an open complement, and now I really need to be a little bit careful because I'm in algebraic geometry, so the only closed subsets I'm even allowed to talk about are those I can talk about in the language of polynomials, perhaps their quotients. So no e's, e the x's or signs allowed, only things cut out by actual equations. And then I'll have a complement, which is an open subset. I'm just going to declare that x is equal to u plus e. And that's it. That's my ring. And now I'll tell you how to multiply. Sorry, that's my group. So if I were to multiply, I'll tell you how to multiply. If to tell you how to multiply two of these guys, then that means I told you how to multiply the ring in general. And so what they are is just the product of the two.
Do you mean that u and z are complementary?
Sorry, they're complementary. That's right. I should have said that. U is the complement. Then the product of the classes is the class of the product. And that's it. The definition is very fast and short. That's it. So let me just do some examples, which are more observations. That the class of a point times anything is itself. So it's the unit in the ring.
Where did you pass isomorphism classes?
Right here.
Oh, okay. I couldn't read that.
Right, sorry.
All right.
So the class of a line is important enough that it has a special name, which is L, which can be short for line or Lefschetz, or probably something else. Lefschetz line. Well, anyway, we'll call it L. And as an example, P2, you can cut up, and again, you should be thinking of your field of choice, CP2, or let's say RP2, because it can be expressed as R squared union R union 1, or CP2 is C squared union C union 1. So we get this is equal to, this is the kind of formula that we can write inside the strip. P2 is L, so L squared plus L plus 1. And if you notice, by writing this down, I've written this in a way that where I'm being agnostic about the field. Okay, so this is the topic. This is the playground in which we will play for the remains of the hour. So let me explore this notion for a second and consider what this means in a situation you may find more familiar in sort of regular geometry. And what do I mean by that? Well, I'm going to be, since this is for motivation, I'm thinking about finite CW complexes, finite type manifolds. So I don't, again, want to be caught up too much in details here because it's for metaphor. And I'll likely say something wrong if I start to have to think it's a blackboard. So if we have a real manifold, then in the land of real manifolds, well, I can take the real numbers, and I can break that up into the negative numbers and the 0 and the positive numbers. And then this is really the real numbers. That's the morphic, if that's the category we're working in. This is the unit. That's a point. There's the real numbers again. So from this equation, the class of R is -1. And more generally, the class of R to the k will be -1 to the k, because this is a ring. And what does this mean? Well, what it means is that we have an arbitrary manifold. We can cut it up into things that are R to the k's and glue them together. And really, this information is the Euler characteristic with compact support. So in other words, this ring, which I haven't given a name, this ring, we call this K, is just the integers. So in one sense, not very interesting. But I want to point out that this is still still non-trivial and interesting. Making this precise involves some very central and important mathematics. Maybe as a first approximation, I want to say just the very fact that on a Riemann surface of genus G, where V minus E plus F is 2 minus 2G, the fact that we can draw a map on a surface, so the faces are contractible, no matter how we draw the map, V minus E plus F always is the same thing, 2 minus 2G. That is embedded in the statement. There's some things which I think of as being rather, we forget how serious they are, but important mathematics are buried in this statement. But the ring is boring. There's seemingly not much going on. And for a future observation, I want to point out that the class, since all getting is the Euler characteristic, but the class of S1, so a circle, or the class of a torus, or the class of 2 circles, are all 0. And I want to compare this to what's going to happen soon in algebraic geometry, in the algebraic situation. Okay, so now let me go to back.
What is the category there?
I'm deliberately vague. I bet you can pick the category you like.
Yeah. Can you just name it?
Okay. I'm going to name it. I'm going to say something wrong, I'm sure. Maybe finite type manifolds. I think it's okay. Okay, so let me go back to my comfort zone and go back to the ring of algebraic varieties, and let me now go temporary. Let me now say that this is going to be more interesting. And the first example will be finite fields, and because with finite fields we have a new set of invariant that should still be interpreted as some kind of Euler characteristic, even a compact and supported Euler characteristic, which that if you have a variety in k to the n, or its enriched version of it, you can just count solutions. This is a finite set. So you have an interesting map from the growth ring, and we call it this, to the integers, which is just you count points. And this makes sense because what really matters is that counting points respects these relations. If you cut x up into 2 pieces, open and close, the number of points in u plus the number of points in z is obviously the number of points in x. And with a little more thought, the number of points in the product, maybe not much more thought, is the product of the number of points in each factor. So that's already something richer, and I should say it already is a clue. But what's that?
So it's a ring homomorphism.
It's a ring. That's right. This is a ring homomorphism. Okay, so now let's go to the complex numbers, where we don't have this, or counting points. We just have infinities. But we still have something for free, which is the Euler characteristic, the compactly supported Euler characteristic. So once we say correctly what this category was, we didn't. The complex varieties do land inside here. Well, they're not even almost manifolds, for example. So in other words, for example, we know, so we can tell from the class of a variety when it's compact and what the Euler characteristic is. And so we know, for example, that CP2 is L squared plus L plus 1 again. And so from this, we know that the compactly supported Euler characteristic is certain.
You keep saying complex squared because you're thinking of cohomology as defining Euler characteristic.
Oh, yes, I'm sorry.
So if you use homology, you wouldn't have to say it.
Exactly. Great. And in this case, it's compact. But we get something more than this. And so this is part of a general theme, which is that if you know that a topological space is not just a general topological space, but you know that it's algebraic, the fact that the space is algebraic imposes more structure than you would think. And as a first example of that, I want to say that you get, in this case, you get only this. But if you're in the algebraic world and your hands are tied behind your back, then you actually get more information. Deligne's theory of weights says the following, implies the following thing, which is that for a smooth, compact, complex projective manifold, you can recover not just the Euler characteristic, the alternating sum of the cohomology groups, but you can recover the cohomology groups themselves. So from this, you get not only that this is H naught minus H1 plus H2 minus H2 plus H4, but instead you read directly off that H naught is 1, H2 is 1, and H4 is 1. And so you get very simple
Additive cohomology.
Additive cohomology. You don't get the multiplicative structure, but you get the with two coefficients, I should say two. And so this is really striking. This uses Deligne's theory of weights. And an example of what's really striking, if you haven't thought about cohomology much in your life and it's also relevant for you, let me just point out what you get from H naught, which is that knowing the class of something in the Grothendieck, the class of a variety, tells you how many components it has. So for comparison, in this case we have, I should put the empty set here. This class 0 can have 0 or 1 or 2 components in different dimensions. But in fact, knowing the class in algebraic, in this sense, if you're algebraic, you know the number of components and you can even work out their dimensions. And you can also even, I should say, you can also tell pod structures. I don't want to go into details because I don't want to define these. So this is I'm not going to bother defining it, but there's additional structures of cohomology you can also recover just by cutting and pasting. In the case that things are smooth and proper, you get things on the nose. If things are, smooth and compact, I want to make sure I use words that are appropriate for a colloquium, for public company. So smooth and compact, you can recover all of these things. But even if it's not smooth and compact, this theory still gives you some predictions or some constraints on the result. Okay, so there is something more in this ring than just Euler characteristic. I should say one should somehow think, though, of what this ring is as some universal generalization of Euler characteristic. That's the so these things are like Euler characteristics. So you should have this somehow in mind. So I now would like to tell you how to think about this ring and what's interesting about it by telling you some things you don't know but might want to know. And some of these, in the literature, these are sometimes called conjectures or speculations or questions. But in this particular area, they all mean the same thing, which is, if it's a conjecture, normally mathematics, when you have a conjecture, it's because you think it's true. And in this case, it's more often if you make a conjecture, one thing I feel quite certain about is conjectures tend to be true or false. And somehow these conjectures are such that if they're proved true, it would be interesting. If they're proved false, it would be interesting. And it's sort of the not knowing that's the problem. So I want to tell so you can
threatened by someone.
What's that?
Are you threatened by someone about stating a conjecture that would end up being false? Johann de Jong once told me we should flog people who stated conjectures that turn out to be false.
I'm going to tell you a conjecture of mine that I believe is false, and others, but there are others that I think are. Here's the reason why you should call it a conjecture if you really think it's important. Because if you want someone to disprove it, then you should call it a conjecture. You say, I wonder if it's true. And something, oh, no, it's not. Then, but they say, we disprove the conjecture of Verrill, and they can take that into that. And they'll be motivated to solve it. Okay. And the thing I want to point out also is sort of the geometry that ends up being involved in the work involved here. So I'll tell you some conjectures, partially because I'll set up some language, and partially because they're inherently interesting, and partially because they're going to come up later on. So the first is the following. It's called the cut and paste conjecture, or decomposability conjecture. This is by Michael Larson and Valerie Weiss in about 2003. It's being restated in various forms by Denef and Moser and others. And to motivate it, let me say that if you have two different varieties, and you can cut them up into this one into 17 pieces, this one into 17 pieces, and they're the same 17 pieces, then they must be the same thing in the Grothendieck ring. Fairly obvious, because you cut them up into the same thing. And the cut and paste conjecture is the opposite.
Would you say that again?
Sure. So if you have two varieties, x and y, say P1 cross P1 and a Hertzsprung surface, another Hertzsprung surface, you can cut them up so that they into the same pieces, by which means this one has some pieces, this one has some pieces, and they match up. They're sort of, the pieces are isomorphic. And the only difference is in the gluing. Then they must be the same class in the weight. That's what's forgotten. So that's the question is going to be. Let me say this right here, which is if x and y are varieties.
Is that the conjecture?
No, let's just take a conjecture. So that's a fact. What I just stated was a fact.
Yeah, right.
And so
definition.
It comes from the definition. So the third question is the opposite, which is that if x and y are varieties, and x equals y in this ring, they have the same Euler characteristics. Is x? Can you cut x up into pieces? And you say this in formula. Piecewise isomorphic. So if you cut them into pieces and have the pieces be isomorphic. So
don't they need to have the same dimension?
That's not fair.
Huh?
No.
Oh, because of that.
No, it's not obvious why. No, maybe this is false.
The dimension is not an invariant of the element in the...
It's not. It's not of a smooth, irreducible thing. Yes.
It is.
But in general, it's hard to say what that.
I mean, it's not known.
It's hard. Well, what do you mean by the dimension? If you take an element of the ring.
No, to start with the variety and take its dimension is an invariant of its element in the ring.
I don't think that's known. Let me think. No, I'm sorry. There's a hard theorem that is known, and it's not clear why that's true.
It's not true?
It is true, but it's not easy.
What?
It's true, but not easy. It's not.
But that violates this conjecture. Oh, no. But they do have to say that. Oh, you have to prove that in order to have this conjecture. Okay, fine. Okay, that's what I was worried about. Okay.
So maybe to be clear, in this example here, these are counterexamples to the conjecture.
Yeah.
In this setting, this really may seem surprising, and just to be clear how it could be wrong, how this could be wrong, you can imagine that there's some space W in which x sits inside and y sits inside, and they're not piecewise isomorphic. Yet somehow the complement of x is isomorphic to the complement of y. That's a way in which this could be false. So somehow, so it could be false. And I should say, it's a theorem. What's more remarkable is that it would require some very clever thinking to prove such a thing. And here's a theorem due to thing mu and Julien Sabag that it's true over the complex numbers if x is a smooth compact surface. Maybe I should say. Yes, I should say complex dimensions. So fourfold. It's also true, or if x has finitely many CP10. I'm saying some informal. Finally, mini sphere, Riemann spheres inside it. Then if one of the two has this, is either this or this, then it's...
It affects its higher dimension.
Yes,
it's
exactly.
not as many CP1s.
Exactly. So it's, I find this interesting because it's...
Yeah, or something.
Yeah, exactly. For example, Claviel, you can identify it by its class symbol. Exactly. If you have Claviel, you can identify it by its, if you have Claviel finally many rational curves, you can identify it by its class. Okay, so that's the first conjectural dimension. The second maybe is more toward a speculation, and let me preface it by saying that there are many clues that nature gives us that tells us that in this ring you want to invert the class of the affine line. You can think of it as the homotopy axiom topology or motivic integration, which I gather there'll be a course on here soon. So there are various clues that you want that nature is telling us to invert one way to divide by n. And I'll give you some examples later on, but for now I just want to mention the conjecture, which is that means you have this ring and you invert, sometimes this is written this way. And then the fear is that you might lose information by this by inverting L. And so here's something which is I think more a question than a conjecture. The conjecture is that you lose no information. And that corresponds to is L a zero divisor? This was asked this was asked by Denef and Lucera, Marson and Lutz, and others as well, Flunen, and I think. And just as a remark, that this ring is not a domain. You can multiply two non-zero things and get zero. And there are two different constructions by Kolar, one by Kolar, Janusz Kolar, one by Bjorn Flunen, showing this is that this behavior is true. Okay, so what I want to say is that if you allow yourself to divide by L, you can start to have things that, let me say that this thing, this relates to a question and a comment that was made a few minutes ago. This carries a filtration by dimension. Every element of this thing is a formal combination of things of different dimension. You can have the subgroup. You can have the subgroup generated by things of dimension 0. That's containing subgroup things of dimension at most 1, containing things at most 2, and so forth. And if you divide by L, you're allowing things of negative dimension. Dimension still kind of makes sense, but you still have such a filtration. And so what I want to do is we're going to, for reasons you'll see soon, we're going to want to work in a completion, which is also, this is the ring where motivic integration takes its values. And rather than really being formal about this, I'm just going to do an example. I think if you see this example, you will understand this ring. I want to be able to write down 1 divided by P1. And that's 1 over 1 plus L. And so what I'll do is I'll say it's 1 over L times 1 over 1 plus 1 over L. And then I can invert this, and I get 1 over L minus 1 over L squared plus 1 over L cubed. And so all I'm doing is I'm allowing myself infinite power series with increasing denominators in L. So this is the ring I want to work in. So it's like varieties, except now you're allowed to invert L and have infinite series in this sense. And that was maybe, I don't know if I should say more about that now or later. You can just stop me. And that's motivated by, that will be motivated.
Most of what you said so far works over other fields.
Absolutely. This is all over any field. And will even be important.
Except for the leads thing.
Yes, or even that can be made. There are things you can do to improve, to say corresponding things in other fields too. Okay, so now I come to perhaps the central character of this talk, the central idea of this talk, which is the following notion, which by all rights should have been invented around 50 years ago. This ring was invented, it's not rocket science, but it was invented by Grothendieck. And so here, the motivic zeta function was defined by Konov in 2001. The paper was published in 2001. So it's a generating function. And all it is it's a generating function for spaces of n points on x. So it's symmetric powers of x. So it's 1 plus xt plus n2xt squared. And that's it. It's very short to say. I want to tell you why it's called the zeta function. The motivic refers to the fact that that takes values, it's a generating function in this ring. So let me just say that if we're working over a finite field, then we're going to get a map to something inside C. And we're going to generate a function over C. We just count points in the symmetric powers. Now I'll tell you what you get when you apply this point counting map. You get the Vey zeta function. And I can't do zetas. Is that a zeta? This is the Vey zeta function. And what this is a generating function for x is a variety over a finite field, and it counts points over not just k, but over all bigger finite fields. It's essentially a generating function, massaged slightly, that is for such a thing. So now, here's why we care about this. What is it just about this? That the Vey zeta function is the subject of the Vey conjectures. And I'll say that the first of the Vey conjectures, or the easiest, the one that was proved by Brook in 1960, is the following thing, which is that this is rational, much of the power series. It's rational, and it's better than rational. Well, what's better than being rational? Well, I'll even tell you roughly what it is, which is, I know most of you know the story fully, but if you haven't, and this is really worth saying really explicitly why this is such an amazing thing. So if this is about things over a finite field, say over Fp, and so if x happened to come from something that lived in regular complex geometry, so it was given by equations over with integer coefficients, say, so it correspond to some complex variety, then that would have topology, or you could reduce the coefficients mod p and get something which has arithmetic. And this is saying that those two things are fundamentally related, and the beginning of how they're related is that this rational function really factors into something where at the bottom we have something where we have a polynomial of degree h0, h1, h2, up to 1 minus t, 2 times the dimension of x, which is the real dimension, 2 times the complex dimension of x. So in other words, let me put this in 2 ways. If you could count point, if you have such a situation, if there's more information about these coefficients as well, that essentially says if you could count points on over a finite field, you know all the cohomology groups. Or if you know all the cohomology groups, you can count points over all finite fields. That's essentially, that's a very striking, that's an amazing thing. And
you need a non-singular x
for that you need a non-singular x, or you need to change your meanings, refine your meanings of cohomology too. Okay, so now I want to take you back to the 40s. And imagine that we didn't know the Vey conjectures were true, its work had not yet proved rationality, and there's no reason why you could not have defined this zeta function back then. And so then we would ask a natural question, which Konov did ask. So it's stated as a fact, but maybe that was an optimistic thing to do, which is it rational? Is this zeta function rational? And it's got, I mean, here's why you've got to believe it's true. This has got to be true. So the question is this rational? And I'll leave aside the mild issue, what I mean by rationality. If that's true, that immediately implies this. Secondly, it implies it for geometric reasons. This turns us into a fact about geometry, I should say, which is very different than the current proofs we have of this right now. Thirdly, now we have to go forward in time, that if you're even over the complex numbers, it makes predictions. And there's a version of this for Hodge structures, which is where you take the shadow, you take the corresponding Hodge structure, whatever that is. And again, I'm not going to define it. And then this is true. And this is Chia's thesis. A thesis of Chia in 1996. He was a student of Bill Fulton. So it's true in that case. We, of course, secretly know that making vectors are true.
Which aspect is true?
So it's true once you take the image, not in this ring, but in an appropriate ring of Hodge structures, which I've not defined.
Well, that's true, though.
Rationality. I'm sorry, I should say rationality is true. More is true, too. Let me say rationality is true. We know it's true when you take its shadow in point counting if you buy Borg's proof. And it tells you even more. Not only will it give you a proof, it tells you something over the complex numbers, which is the following thing. Which is, if I tell you I've got a power series, and I tell you it's rational, it's a fraction, then by what you learned many decades ago, or years ago for some of you, then what this means, you have a recursion for the coefficients of this generated function. If you're rational, it's multiplied by the denominator. What it means is if you know the first few symmetric powers of x, you know the information of it in this ring, which means you know a lot of information about it, then you know everything about all the symmetric powers. And how far you have to go depends on the topology of x. So that would be, you've got something else that's rather fundamental about complex manifolds, which would tell us a lot. So I feel like for moral reasons, if the universe is a just place, this has got to be true, and it's the right way to prove the main conjecture.
Is this original Grothendieck ring countable?
Not over C. Not over C, no. Okay, so this has got to be true. So I want to mention a theorem I mentioned once in 2003, which is false. So it is not rational, and they had to be extremely, this requires some sort of cleverness, regular. I mean, it's a really remarkably clever paper to be able to find if all reasonable ways of getting at this ring suggest that it's rational, they need to develop a new way of thinking about this ring. And then this is just what I think is an important question, which I will not follow up on this talk, which is that the question is if it's not rational here, somewhere between here and here becomes rational. And I think it's an important question of where between here and here, what's the cohomology theory, roughly speaking, right? Not in a technical sense, but in a sense that can be made precise, where it starts to become rational. And for example, maybe if you invert L, it becomes rational, and that would give a proof of the Veil conjectures.
The no is for which fields?
The no is for, good question. I think it's any field.
What?
Any field. It's never rational. That is actually a good question. At least I'm 100% sure for the complex numbers, for comparison 0. I think it's true for any fields, but I need to think about this expression. Okay. So now let me tell you a new conjecture that is intended to suggest to be in the same spirit and motivated partially by what I've said so far. So the motivation in this case is going to be both topological and arithmetic. Okay, this is.
What does the word motific have to do with this entire?
So this ring is sometimes called the ring of ring of motives or ring of baby motives. And it's
whatever that word means.
Whatever that
means.
This
ring.
And it's even slightly misleading name.
Okay.
And this is with Melanie Wood. And so let me say it informally, and then tell. So in topology, that setminus of x Symmetric X in an appropriate sense converges. Now I want to make that precise, but in a sense that's better for me. That if you take more and more points on X, the resulting space topologically converges to, and the Dole-Tom theorem tells you what it converges to. So it is a hypothesis that X is geometrically irreducible. I'll write that in small letters so you don't pay any attention. It is a hypothesis that requires you to know the meaning of the word, but it's not an important thing. And so here's what I want to do.
I couldn't follow all that. You said it fast.
So pretend I didn't say that. So it's something I don't want to get into, but it's not important. So here's what I want to say. Except, as is already pointed out by comments that is already made, that this changes, these are different dimensions. So let me normalize it. And then this has to live somewhere where I invert L. If I want the limit, I better take this completion in the sense of this. Okay, so there's the statement. But now let me unpack it for you so you can have a sense as to why you should potentially believe it. The first thing is that initial topological motivation. And what this kind of does is it turns homology to cohomology. But let me say this is the natural first guess as to what would be the algebraic geometric analog of the topological fact that Synapse X stabilizes. It's also sometimes true for varieties that are rational. This means varieties that have a big open subset that look like n space. It's also true for curves, so long as they have a rational point, but I won't bother writing that down. It's also true when you look at Hodge structures. If you look at Schneider or Hodge structures, whatever you mean. It's also true when you specialize the point counter. Although this is somehow a moral statement, not a logical statement. And it's also true there's further topological motivation from the Dole-Tom theorem that I will invent. And maybe the almost last thing I'll say is that it's even motivated, it's also motivated, and I'll say a little bit about this because it's entertaining, by the Bay conjectures. And I'll say why, because this gets us back to calculus, freshman calculus again. That if you look at this formula here, if I give you a rational function, and I tell you, if I give you a power series, and I tell you it's a rational function, I say, how do the coefficients grow? You would say, well, as n gets large, how do they grow? Well, I look at the largest inverse root, and they'll grow like powers of that. And then if you parse what this says and make a correct definition of largest, there's the coefficient. And that's actually the largest root, inverse root in some sense. So that's a reasonable thing too. So this is all, in some sense, strong. Perhaps you might look at this as good evidence for this wanting to be true. And then maybe another reason to consider it is the following theorem by Daniel Ritt last year, which is that this contradicts the cut and paste conjecture. In other words, it cannot be true at the same time as the cut and paste conjecture. It also contradicts the L non-zero divisor conjecture. In other words, any one of these conjectures would kill the other conjectures. So this makes you, I'd be equally happy disproving it as well. Okay, so that's the. I should say I want this to be true because it would suggest so much.
So do you know it's a Cauchy sequence, or at least being able to say what the limit is, or if you know that?
No, we do not know that it's Cauchy. I mean, yeah, it's equivalent. If you knew it was a Cauchy sequence, you would converge.
Maybe because you can do it.
Right. So that's and in lots and lots of cases, in any case you get a hold of it, it is a Cauchy sequence. Okay. So now I told you a lot of things we didn't know. And so now I want to take you to something which I thought I knew, which are points on a line. So what I'd like to do is consider n points on a line, which I'm going to call C, and I'll call A1, depending on what field I want to be on. And so if I have n unordered complex numbers, that's parameterized by n ordered complex numbers. Because to know n unordered complex numbers, All I need to know are the coefficients of the polynomial within its roots. So in other words, this is parametrized by an. So sim n of a1 is an. That's what I'm saying. And inside this we have the discriminant. Let me write it this way. Delta is for discriminant. What I mean is that the n roots come in, they could come in one pair and then n minus 2 singletons, or they're closure. I want these to be closed subsets. But more generally, any root pattern, given any partition of n, I could have a root pattern where I could say, for example, a good one will be, that's going to come up, is that I can want an m-fold root or worse. That's what this means. So this is the language I want to use. And I want to give you 3 parallel results in different fields. None of which, to show you, to give you a hint that something interesting is going to go on. So let me look at, basically what I look at is an. I want to look at those polynomials with no double root. So wait, the discriminant complement. And so in arithmetic, let me start over F2. Let me ask the question, which is, how many polynomials over F2, monic polynomials over a finite field, have no repeated root? And let me put it differently. What's the probability, since there are only finite many polynomials over a finite field, what's the probability that there's no double root, or that there is a double root? So the probability of a double root is amazingly 1 over q, as long as n is at least 2. Well, if you want no m-fold root, it's 1 over q to the n minus 1. And this is something which I think you might have a clever argument. So I'll say it as an exercise, but I don't mean it will be an easy exercise. But there's a clever, short way to do it. And I should say that I think of 2 ways of doing it. And if you do it one way, you're born to be a number theorist. If you do another way, you're born to be a geometer. And so you will reveal your true nature by answering this question. So now we're going to say in topology, I want to mention the Theorem of Arnold. Which says, well, I can't count points. I'll just take cohomology groups. I'll tell you the cohomology group of the discriminant complement. Let me do this more complicated discriminant complement, the more general one. And his theorem implies it can be used to show this, which is that it's mostly 0, except h0 is 1, and h2m minus 1 is 1. And it's 0 otherwise. This is cohomology with few coefficients. So why is this the same as this? What it means, the probability of not having double root is 1 minus 1 over q. Or in this case, not having double root, it's 1 minus 1 over q, then minus 1. What I want to say is when you squint, then the 1 should be this, and this should be this. And that this is not a load of crap I'm giving you. This is really something that you should believe to be true. The more correctly, this was proved by Arnold around shortly before 1970. This could have been done a long time earlier. And we should have been able to tell Arnold what the result was going to be before he proved it. But of course, he's Arnold, so he proved it first. He was better. So, and now the algebraic geometry version of this, let me fit this on this part of the board, and I want to connect it, is what connects these, is that this discriminant subroutine, hypersurface in case n is 2, you can cut and paste it to the affine space. And that's a really explicit question you can ask a high school student. And I think in certain classes, some people in this room were that high school student. You could ask them, they would have answered it. This is really very explicit. You could just ask them to cut this thing up, this set. Don't use the word algebraic variety. You rearrange it to get flat space. And this is but I think it's a hard. This now enters the something. This is actually quite tricky. Okay, now let me take this as a starting point. And my starting point is that, well, current, for quite some time, there's been this theme coming out of topology and leaking into many other subjects of stabilization. That's been extremely enlightening. So in this case, in this baby case, I want to follow this through. So I want to say as n gets large, as the number of points gets large, these answers stabilize. So in the case of arithmetic, I'm saying as n gets large, this stabilizes. Well, that's stupid, of course. It's constant. There's not much going on there. As n gets large, this stabilizes. Well, this looks stupid because there's no n in the picture. But it's not stupid because whenever you have a stabilization result, usually you have a map from one space into another space. And it's not just that the numbers stabilize, but it means something better. And let me say, for the sake of time, just in words rather than writing on the board, that here's the correct statement. The correct way to see this in this context, which is, if I said, consider the space of all polynomials in one variable with no n-fold root. Let me say with no double root, just to make my life simpler in this example. All polynomials in one variable with no double root. Then its cohomology groups are this. And furthermore, if I'm interested in the monic polynomials of degree n, it sits inside this big space, and I claim it's a homotopy equivalence as soon as the degree is at least 2. And you may stop me and say, wait, how do you topologize this space? And the answer is, well, just go ahead and you figure it out. There's only one reasonable way to do it, and you'll be right. And so then you get something which is a true theorem, and it stabilizes. And then in algebraic geometry, similarly, this stabilizes when you interpret it the correct way. And now let me say something. Let me give you a clue that this is the beginning of something more complicated, which is that you can now look at more complicated discriminants, first of all, and then, of course, more interesting topology. Affine spaces notoriously little topology. So I should say, first of all, when you add more, once you add more, look at more complicated discriminants, then you can say in algebraic geometry what the limit is, what it stabilizes to. But you can no longer make it work in topology. The topological methods no longer work. I can give you some explicit examples that can be seen as conjectures that are predicted by the algebraic geometry that the topological methods cannot get hold of. The first one will be, look at the space of all polynomials. Well, look at the case of 2 double roots or worse. That's the first case that cannot be applied. Okay, so now let me sort of state the form of a general statement, which is one of the 2 results I wanted to mention, now that I think we're well set up for it, which is, we've got this case, so I want to now work on a general and so not the affine line, and so I've been talking about configurations of points with various various multiplicities on X. So I could ask for 2 of the points to collide, or 3, or m, or different sets to collide. And maybe you might think, quite reasonably, that it might make sense to look at the open cell, where the points don't collide further. I want to describe a root pattern, a point pattern, and let them degenerate. But normal people would think about the case where you have a certain root pattern. And let me say in topology.
Is X non-singular here?
No. Oh, for topology, sorry. In topology, it's going to be non-singular. For algebraic geometry, it's not going to be non-singular. So let's say X is non-singular. So what I want to do is consider the stabilized problem, let the number of points go to infinity and have some multiplicities. And then I should say that in the case of that recent Inventiones paper of Tom Church, may not have appeared yet, and also work of Randall Williams, whose name I'm going to spell, because I forget how many letters he has. So this is within the last year or 2. They can say what this stabilizes to in a rather explicit sense. However, you need to glue many of these strata together, and so nothing can really be reasonably, nothing can be said topologically currently here. So the point I want to make is that in algebraic geometry, both of these can be stated completely within this Grothendieck ring. And in particular, quite explicitly. And these answers, and I should say that really one moral I want to say is that this is the better answer. It's somewhat strange that it's the closure that behaves better. This is the opposite of the way it usually is. But the answers are in terms, again, for my sake of time, I won't say much more, in terms of motivic zeta functions. Or motivic zeta values. So you can write explicitly any of these limits, and again, it's only the limit that they become motivic zeta values only as being taught by the topologists. Things become nice only when the number of points goes to infinity. So let me conclude.
So what is being described here, the topology, and that box?
What's described? So
what is being described? Down there's the Grothendieck,
right? So up here, they can say the cohomology groups of any cohomology group of any spaces. And if an explicit recipe comes to representations. Okay, so let me generalize this in a different direction. This is about points. It's also about hypersurfaces. So I'd like to, maybe for the sake of time, I'm only going to motivate it about stating. I want to say the cognate result about hypersurfaces, which is very cognate to this picture here. And I'd like to give 5 motivations. As to why you should expect something interesting for different parts of mathematics. Maybe the 0th order, is that the case of the points on the line you can do? And again, I didn't say much more, but I didn't say much about it, but that this generalizes vastly and some pattern is clearly going on. That's the first one. The second is maybe one for arithmetic. It's a fact that they've known for a long time, which is what's the probability if I give you an integer, a random integer, what's the probability it has no prime, no square, no non-trivial square? What's probably a square free? No repeated prime factor. And the answer to that, first you have to figure out what the probability measure is, but then that's okay. Whatever you figure out will be right. And then what's the probability that an integer, random integer is square free? It's 6 over pi squared. It's 1 over zeta of 2. A centuries-old result. So here's a third result that I want to use to motivate the final statement, which is the theorem of Arnold. Which is given a smooth, I'm going to need smooth, projective, consistent projective space over a finite field. And it sits inside some projective space. And then you could ask, what's the probability that a degree D hypersurface meets it smoothly, transversely? And I'm saying this somewhat telegraphically. And the answer is that he doesn't know. That's not the full answer. But he knows that the right thing to do is to let D get large, and it tends to a limit. So there are finitely many hypersurfaces over a finite field. This is an honest probability. So you take the limit, and it's 1 over a zeta value, then a J zeta value. And the fact that these look similar should be very suspicious. And so let me say. So let me say just one more motivation, which is a theorem of Vakil, best expressed in his ICM lectures, lecture on the topic, which is that if you look on C to the n, and you look at the space of smooth divisors, smooth hypersurfaces. What's that? So smooth hypersurfaces in C to the n, that's a space, it's a topological space. And its cohomology groups are, it's got only 2 non-zero cohomology groups. It's got an H naught and one other one. I forgot what it is, but it's very analogous to, you should look at Arnold's results and see if this is relevant. So these 5 things are all suggestive. Well, the last one has to do with Gauch's conjecture, which I'll note, that there should be a corresponding theorem in the Grothendieck ring which will imply or be parallel to many of these. And the answer is that, well, first of all, yes, there is. It's explicit. The answer is given in general for general x, that for any number of singularities, in terms of motivic zeta functions, one features that if you, like me, prefer to think about these overly complex numbers, then the proof itself requires going to finite fields. So if you're a geometer, you're forced to think about arithmetic in the same way that if you're an arithmetic person, you're forced to think about geometry. And the last thing I'll say is that the formula is if you squint and change some of the zeta values, change one of the zeta values, the answer to this question is exactly the same. When you look for hypersurfaces with m singular points, is exactly the same as looking at points with m points fleshed out as well. So these answers are even the same, but there's nothing parallel in the proofs at all. Okay, so let me just sum up, since I said everything I wanted to say. So so there are sort of three ways of looking at the kinds of problems I've been discussing. There are arithmetic geometric versions. There's arithmetic versions, like put in the result, for example, or 1 over zeta 2. There are geometric statements, topological statements, like I think of Vasilyev's and Arnold's. And there are algebraic geometric statements where you work inside this Grothendieck ring, which captures some, but not all, of the things, of the aspects that you can see in topology and arithmetic. And so the talk, what I want to get across is about a series of results in this area that connects these three. It's about cognate, that's in algebraic geometry, that is cognate to things that we know that are beautiful and very interesting in these other areas. And probably the theme of the final theorems is that these things, as the topologists have taught us, the topology, or the algebraic version of topology, stabilizes somehow, becomes better behaved as the problem you're considering goes to infinity. Maybe the last thing I want you to really most remember, just that the idea of this Grothendieck ring is a really basic one about cutting and pasting, which is maybe doesn't give you a whole lot when you're dealing with traditional manifolds, but when you're in an algebraic setting, it ends up being surprisingly strong and interesting. Okay, thank you very much for your time.
More questions? That's a remark to me.
Sure. So Vasilyev's remark. Vasilyev, this is a sample, but he has a whole collection which are, at least for me, fantastic. So this example is this: you take C to the n, take all smooth in the literal sense, hypersurfaces in C to the n. Take the space of all of them, and take the cohomology of that space. This has only h naught and one other h, I forget which, and they're both one-dimensional. And the comparison I want to make was
like that. Like Arnold.
Exactly.
They just did the Arnold.
Ah, great. Oh, okay. I knew they were in the same school. I didn't know. Great. I mean, I come to the right place there.
More questions?
So you have this zeta material zeta function which is not rational. So can you talk about its zeros of this zeta function?
So what I'd like to do is talk about, I should say what Daniel Lipp can do more of this than I can, is talk about the zeros and the size of the roots. Then you need to make sense of size. And so maybe in the case when it is rational, there are some cases where we can see that the size of roots are what you'd expect. But the interesting case is when it's not rational, what's the right question? Where are the poles? I would say that what do you say if it's not rational? And one thing you might say is you could get some sense, you could take radius of convergence to get an idea of the size of roots of the denominator, or you could invert it and take the radius. So I think the question is very much a right one, and our understanding is extremely limited.
But there is no analog for both.
In the case of curves, there's an analog which is true. In the case of surfaces, there's the right statement. I think it's right to say that there's no rigorous statement of what the Riemann hypothesis should be for these but I think there should be. When I say there's none, not because there can't be. I just think that's actually what Litt is trying to do right now.
Well, if there are no questions, let's thank Ravi again. There will be a